Hello, and welcome back to Science for Sleep. I am so glad you have found your way to this quiet corner of the universe. Whether you are curled up in a warm blanket or simply searching for a moment of stillness after the turning wheels of a long day, know that you are always welcome here. Before we begin, let us share in a small thought experiment. Feel the solidity of the bed you are lying on, or the chair you are sitting in. It feels real, doesn't it? Solid and dependable. But what if I told you that this solidity is just a beautiful illusion? That beneath the familiar surface of reality lies a foundational world, a world woven from a mist of potential, where our conventional rules no longer apply? In our journey tonight, we will take a deep dive into a reality where the normal laws are broken. A world where a single particle can be in many places at once, where two particles a galaxy apart can still speak to each other instantly, and where our very act of observation is what decides what is real. But this is not just a journey into the strange. This is a story of how humanity is learning to tame that chaos. We will explore the incredible breakthroughs of the last few years, how we are now building computing machines of unimaginable power, sensors that can see the invisible, and a new horizon of technology that is opening up right before our eyes. This is a journey from the deepest mysteries of reality to the remarkable technologies that will shape our future. Tonight's journey will take us to the very foundations of reality, a place filled with ideas both strange and beautiful. I believe our shared exploration will make this trip all the more profound. So, as a question or a spark of thought arises in your mind, I invite you to share it in the comments below. Let us make this a space for our community to discuss and wonder together. And if this deep dive into the quantum mist sparks your curiosity, a gentle tap of the like and subscribe buttons helps our community continue these voyages together. As always, I would love to know where you are listening from in the world. Please feel free to leave a quiet greeting. Now, let your mind become free. We are about to begin. Our journey into the hidden world begins not by traveling outwards, towards the distant, glittering stars, but by turning our gaze inwards. It is a journey of scale, a quiet descent into the very heart of the matter that makes up our world and our own bodies. We must shrink our perspective, smaller and smaller, past the limits of what our eyes can see, past the intricate world of cells and molecules, until we arrive at the fundamental building block of everything we have ever known, the atom. For a long time, our picture of the atom was a comforting one. We imagined it as a perfect, miniature solar system. At its center was a dense, heavy nucleus, like a tiny sun, and orbiting around it were the electrons, like faithful little planets held in their paths by invisible forces. It was a neat, orderly, and mechanical universe in miniature, a world of predictable orbits and solid particles. This picture was beautiful, and it made sense. It reflected the solid, dependable world that we experience every day. But at the beginning of the 20th century, a series of quiet experiments began to reveal that this comforting picture was profoundly and beautifully wrong. The story of this revelation begins with a scientist named Ernest Rutherford, who, in 1909, decided to probe the structure of the atom. He did this by firing tiny, positively charged particles, like incredibly small bullets, at a piece of gold foil that was unimaginably thin, only a few hundred atoms thick. He expected that these tiny particles would pass straight through the foil, perhaps being slightly deflected, as if he were firing a rifle through a thin piece of paper. And for the most part, that is exactly what happened. Almost all of the particles sailed through as if nothing was there at all. But then, something completely unexpected occurred. About 1 in every 8,000 particles did not pass through. Instead, it bounced back, ricocheting off the foil as if it had hit something solid and immensely powerful. Rutherford would later describe his astonishment. He said it was as if you had fired a 15-inch shell at a piece of tissue paper and it came back and hit you. This single, shocking observation shattered the old model of the atom forever. The only way to explain this result was if the vast majority of the atom was, in fact, completely empty space, and that all of its positive charge and almost all of its mass was concentrated in an incredibly tiny, incredibly dense point at its very center, the nucleus. And this is the first great, and perhaps unsettling, mystery we encounter on our journey. The atom, the fundamental building block of the solid world, is almost entirely empty. The sheer scale of this emptiness is difficult for our minds to grasp. Let us try with an analogy. Imagine that the nucleus of a single hydrogen atom, a single proton, was the size of a small marble, placed on the center spot of a vast, empty football stadium. The atom's single electron would not be another marble orbiting nearby. It would be a single speck of dust, so small as to be almost without dimension, drifting somewhere in the highest, most distant seats of that same stadium. Everything in between is empty space. The chair you are sitting on, the walls of your room, your own hand, they are all made of these tiny, empty stadiums. So why, then, does the world feel so solid? Why can you not pass your hand through the wall? The answer is the true ghost in the atom. The solidity we feel is not the result of solid things touching solid things. It is the result of invisible forces, pushing against each other in that vast emptiness. The electron is not just a speck of dust. It is a carrier of a negative electrical charge, and this charge creates a vast field of influence around it. When the electron cloud of an atom in your hand approaches the electron cloud of an atom in the wall, these two clouds, both negatively charged, repel each other with immense force. What you feel as the sensation of solid touch is not contact. It is the powerful, invisible, and ghostly cushion of the electromagnetic force. You have never truly touched anything in your entire life. You have only ever felt the force fields of its atoms, pushing back against the force fields of your own. The solid, dependable world is a beautiful illusion, a sensory story told to us by these invisible ghosts. The universe, at its most fundamental level, is not made of stuff in the way we think of it. It is made of relationships, of fields of influence, of whispers of force across an immense and silent void. This emptiness is not a void of nothingness. It is a stage, a vast and quiet arena of pure potential. And it is within this ghostly emptiness that the even stranger and more profound rules of the quantum world begin to play out, rules that will challenge our very understanding of what it means for something to exist at all. And so, we find ourselves standing on the vast and silent stage of the atom. We have journeyed inward, past the illusion of solidity, and discovered a realm of almost unimaginable emptiness, a ghostly space where invisible forces create the world we know. This emptiness is not a void of nothingness. It is an arena of pure potential. But this raises a quiet and profound question. In all of that vast, empty space within a single atom, what is the electron actually doing? In our old, comforting picture of a miniature solar system, the answer was simple. It was orbiting. It was a tiny planet on a predictable path, a neat and tidy circle around its nuclear sun. But the strange message from Rutherford's experiment, the message of the emptiness, told us that this picture could not be right. The rules of this inner world were different. Modern quantum mechanics gives us a new picture, one that is far stranger and far more beautiful. The electron, in its vast atomic stadium, is not a solid little ball following a definite path. Instead, it is better to imagine it as a cloud of probability, a delicate, shimmering haze of potential existence. It is not in any one single seat of the stadium, but rather, its presence is smeared out across the entire arena, more likely to be found in some areas, less likely in others, but never, ever in one definite place. This strange state of being, of existing in multiple possibilities all at once, is known as quantum superposition. It is perhaps the most fundamental and the most famously strange rule of this hidden world. To help our minds grasp this idea, let us leave the atom for a moment and return to our metaphor of music. Imagine a single, silent string on a grand piano. Before it is played, what note is it making? The answer, in a sense, is that it is making no note at all, but in another, more profound sense, it holds within it the pure potential for every note. Its existence is a quiet, humming superposition of all the beautiful sounds it could possibly create. It is not yet a C-sharp or a G-flat. It is the possibility of all of them, held in a state of perfect, unresolved harmony. Only when a finger or a hammer strikes the string only when an observation is made. This wave of potential collapse into a single definite reality. The unplayed melody becomes a single, clear note. This is precisely how we must picture the electron. Before we try to find it, before we strike the string by performing a measurement, the electron is not in one place. It exists in a superposition of all possible places it could be within its orbital cloud. It is not here, nor is it there. It is a wave of pure potential spread throughout the vast, empty stadium of the atom. The very moment we try to measure its position, the very instant our consciousness, through our instruments, asks the question, "Where are you?" the universe responds. The wave of potential collapses. The unplayed melody resolves into a single, clear note, and in that instant, and only in that instant, the electron appears in one single, definite location. But which location? Which note will the universe choose to play? This is another layer of the mystery. We can never know with certainty. We can only know the probabilities. The places where the electron's probability cloud is denser are the places where it is more likely to appear when we look. But the final outcome of any single measurement is, and will always be, completely and beautifully random. Let us allow that thought to settle. The very foundation of our solid, predictable world is governed by a law of pure potential and pure chance. The universe, at its core, is not a great clockwork machine, ticking along a predictable path. It is a grand and mysterious symphony of possibilities, a collection of unplayed melodies that only resolve into the concrete reality we know when they are observed, when they are measured, when they interact with the world. The solid chair you feel is real only because an uncountable number of its atoms are constantly interacting, constantly collapsing each other's waves of potential into a stable, collective form. But each individual particle, on its own, remains a ghost, a whisper, a beautiful and unresolved chord of pure possibility. This idea challenges our most basic intuitions about the world, but it is not something to be feared. It is, perhaps, a more beautiful way to see the universe. It suggests that reality is not a static, predetermined script, but a dynamic and creative performance, a world of infinite potential that is being written and rewritten in every single moment. But this leads us to an even deeper and more unsettling question. If the act of our looking is what forces this world of potential to choose a single reality, then what does that say about the role of the observer? What happens in this strange and beautiful dance when we decide to watch? We are left with a quiet and perhaps unsettling question. If the world at its most fundamental level exists as a shimmering cloud of potential, an unplayed melody of possibilities, and if the act of our looking, our simple act of measurement, is what forces this world to choose a single definite reality, then what does that say about the role of the observer? What happens in this strange and beautiful dance between what is and what could be when we decide to watch? This is the doorway to one of the most profound and most debated mysteries in all of science. It is known as the observer effect, and it suggests that we are not, and can never be, separate, passive viewers of the universe. We are, in a very real and fundamental way, participants. The act of observation is not a passive glance, it is an active engagement, a dance between the observer and the observed. To understand this dance, we must look to the most famous and beautiful experiment in all of quantum physics, the double-slit experiment. It is, in its essence, very simple. Imagine a barrier with two thin, parallel slits cut into it. Now, imagine firing single electrons, one at a time, towards this barrier. Behind the barrier is a screen that will light up wherever an electron hits it, allowing us to see the final pattern. First, let us perform the experiment without watching. We fire the electrons one by one, but we do not place any detector at the slits to see which path each electron takes. We simply wait, in quiet patience, and watch the pattern build up on the screen behind. If electrons were simple, solid particles, like tiny marbles, we would expect to see two simple, bright lines on the screen, a line behind each slit. But that is not what we see. Instead, a beautiful and impossible pattern emerges. We see a series of many bright and dark bands, an interference pattern, like the ripples created when two pebbles are dropped into a still pond. This pattern is a definitive signature of a wave. A wave can pass through both slits at once, and the two resulting waves interfere with each other, creating peaks where they add together and troughs where they cancel each other out. The only way this pattern can be created is if each single, solitary electron somehow passed through both slits at the same time. In its unobserved state, the electron was not a particle. It was a wave of potential, a superposition of all possible paths, and it behaved as such. Now, let us repeat the experiment, but this time, we will watch. We place a tiny, gentle detector at the slits, a silent watcher whose only job is to tell us which slit each electron actually goes through. We are now observing the path. We are asking the question, which way did you go? And in that moment, everything changes. The very instant we begin to watch, the beautiful, wave-like interference pattern on the screen vanishes completely. It dissolves away, and in its place, we see two simple, bright lines. A perfect match for the pattern we would expect from tiny, solid marbles, each one passing through only one slit or the other. The electron, it seems, knew it was being watched. The simple, gentle act of our observation, of our asking the question, forced the wave of potential to collapse. It forced the electron to abandon its ghostly, wave-like nature and behave like a simple, definite particle. It forced the unplayed melody to become a single, clear note. This is the heart of the mystery. What does it mean for the universe to know it is being watched? For a long time, this led to deep philosophical speculation about the role of human consciousness in shaping reality. But a more subtle, and perhaps more beautiful, understanding has emerged. It is not our mind itself that changes the world, but the physical act of measurement. To see which path an electron takes, we must interact with it. We must bounce a particle of light off of it, or feel its magnetic field. And that gentle touch, that tiny interaction, is enough to break the fragile soap bubble of its quantum state. It is enough to end the dance. It brings to mind the old philosophical riddle. If a tree falls in a forest and no one is around to hear it, does it make a sound? The quantum world asks an even deeper question. If an electron is not observed, is it even in a single place? The answer of quantum mechanics is no. When unobserved, it is only a wave of potential. This does not mean that reality is not real. It means that reality is participatory. The universe is not a static movie we are simply watching. It is a dynamic and interactive dance, and we are its partners. The world is a conversation between the potential and the actual, and every measurement, every observation, every single interaction is a part of that ongoing conversation. We are not separate from the cosmos, looking in from the outside. We are a part of the cosmos. And our interactions with it, our gentle gaze, helps to shape its reality, moment by moment. This dance, this intimate connection between the observer and a single particle, is profound enough. But what happens when we observe a particle that has a mysterious, unbreakable connection to another, a twin soul that could be a universe away? What happens to the dance then? This dance, this intimate connection between the observer and a single particle, is profound enough. It reveals a universe that is not a static picture, but a participatory performance. But what happens when we observe a particle that has a mysterious, unbreakable connection to another, a twin soul that could be a universe away? What happens to the dance then? Here, we step through the final doorway, into the deepest, most beautiful, and most famously strange mystery of the quantum world. It is a phenomenon so bizarre that it deeply troubled even Albert Einstein, the very architect of our modern understanding of space and time. He famously called it spooky action at a distance. We call it quantum entanglement. To understand it, let us imagine not one particle, but two, born from the same single event. Perhaps a single, unstable particle has decayed, creating a pair of new particles that now fly away from each other in opposite directions. In the quantum world, these two new particles can be created in a special, intimately connected state. They are entangled. Think of them not as two separate individuals, but as two sides of the same coin, or perhaps as two volumes of the same single book. They are forever part of the same story. Whatever is true for one is, in a perfectly correlated way, true for the other. If one particle has an upward spin, a quantum property like a tiny magnetic orientation, then its entangled twin, no matter where it is, must have a downward spin. The system as a whole has a perfect, balanced harmony. But remember the rule of superposition. Before we make a measurement, neither particle has a definite spin. Each one exists in a ghostly cloud of potential, a perfect superposition of both up and down at the same time. The coin has not yet landed. The story in the book has not yet been read. Now, let us allow these two twin souls to travel. Let one journey for a second, a year, 1,000 years, until it is on the far side of the galaxy, light years away from its twin. They are now separated by an unimaginable gulf of space and time. And now, here on Earth, we decide to observe our local particle. We make a measurement, asking the question, what is your spin? In that instant, as we know, the wave of potential collapses. The unplayed melody becomes a single note. Our particle randomly chooses a state. Let us say it becomes spin up. Here is the heart of the mystery. The very instant that our particle makes its choice, its twin, on the other side of the galaxy, also makes a choice, instantly, with no delay. It immediately collapses its own wave of potential and becomes spin down. This connection is instantaneous. It is a conversation that seems to transcend space itself. Information, the knowledge of the first particle's state, seems to travel across the galaxy faster than the speed of light, violating the most sacred and fundamental rule of Einstein's universe. This is what so deeply troubled Einstein. He believed that nothing, absolutely nothing, could travel faster than light. This instantaneous connection felt like a cheat, a form of cosmic magic that broke the rules of reality. He and his colleagues proposed a more sensible, classical explanation. Perhaps, they argued, the particles were never in a state of superposition at all. Perhaps they were like a pair of gloves, separated at birth and placed into two identical boxes. One box is sent to you, the other is sent across the galaxy. You do not know which glove you have until you open your box. When you open it and find the left-handed glove, you know, instantly, that the other box contains the right-handed glove. No spooky action is needed. The information was always there, hidden from you, but predetermined from the very beginning. This idea was called the theory of hidden variables. For decades, this debate remained a philosophical one. The spooky, instantaneous connection versus the sensible, predetermined gloves. There seemed to be no way to perform an experiment to tell which was true. Until, in the 1960s, a brilliant physicist named John Bell did the impossible. He devised a beautiful mathematical theorem, a clever statistical test that could, in principle, distinguish between the two realities. His work predicted that if you made many measurements of entangled particles at different angles, the patterns of correlation you would find would be different depending on which theory was correct. If the universe was classical, like the gloves, the correlations would have a certain limit, but if the universe was truly spooky, those correlations could be stronger, breaking Bell's limit. And in the decades since, experiment after experiment, with increasing and now unquestionable precision, has been performed. And the verdict is in. The universe is, indeed, that strange. Bell's limit is broken. Again and again, the spooky action at a distance is real. This does not mean we can send messages faster than light. The outcome of each individual measurement is still random, but it does reveal a deeper, more holistic layer of reality. It suggests that at some fundamental level, the universe is not a collection of separate, local things. It is a single, interconnected, and non-local whole. The two particles, even when separated by a galaxy, were never truly separate. The space between them, in some profound way, did not exist. The separation we perceive in our everyday world might be, in some sense, an illusion, and in that thought, there is not fear, but a profound and beautiful sense of connection. We are not isolated islands of being. We are all, at the most fundamental level, woven from the same single, unbroken, quantum fabric. And this strange, beautiful fabric is not just a philosophical curiosity. It is the very material from which a new age of technology is now being built. We have arrived at a place of profound connection. We have learned that the universe, at its most fundamental level, is not a collection of separate, isolated things, but a single, unbroken, and interconnected whole. The strange and beautiful rules of superposition, the observer effect, and quantum entanglement paint a picture of reality that is ghostly, participatory, and woven together by invisible, instantaneous threads. And yet, as you lie here, in the quiet comfort of your room, this picture may seem like a distant dream, a piece of abstract poetry that has no bearing on your own experience. The world around you feels solid, definite, and predictable. The chair does not exist in a superposition of multiple locations. It is simply there. The book on your nightstand does not decide its properties only when you look at it. Its story is written and unchanging. And the particles that make up your own body do not seem to be spookily entangled with particles on the far side of the galaxy. This raises the great and obvious question. If the universe is truly governed by these strange and beautiful quantum laws, why do we not see them? Why does our everyday world, the world of tables and chairs, of trees and stones, seem so resolutely classical? Why does the magic of the quantum realm seem to fade away as we zoom out from the world of the atom to the world of our own experience? The answer to this question is the great challenge of the quantum world, and the single greatest hurdle that scientists must overcome to build the technologies of the future. The answer has a simple and rather beautiful name: decoherence. To understand it, let us return to a metaphor. Imagine that a pure quantum stata, single, isolated particle in a perfect superposition is like a perfect soap bubble. It is a thing of exquisite beauty and profound fragility. Within its shimmering, iridescent surface, it holds a world of potential. It is a perfect sphere, reflecting all possibilities at once. It is a delicate, self-contained universe of pure potential. Now, imagine what happens when anything from the outside world touches this perfect bubble. A single mote of dust, a gentle breeze, even the lightest touch of a finger, the bubble instantly pops. The beautiful, shimmering sphere of potential vanishes, leaving behind nothing but a few tiny, mundane droplets of soap and water. The magic is gone. This is decoherence. The quantum state is the perfect soap bubble, and the outside world, our classical, noisy, and chaotic environment, is the finger that is constantly reaching out to touch it. Any interaction, no matter how small, between our quantum system and its surroundings, a single stray particle of light bouncing off of it, a tiny vibration from a nearby atom, a slight fluctuation in a magnetic field acts as a measurement. It is an act of observation, and this single, tiny touch is enough to pop the bubble. In that instant, the quantum state decoheres. The beautiful wave of potential collapses. The superposition of multiple states is destroyed, and the particle is forced to choose a single, definite, classical state. Its spooky entanglement with its twin is severed. It loses its quantum magic and becomes just another simple, predictable part of our classical world. Now, let us scale this idea up. Why don't you see a chair, or a cat, or even a single grain of dust exist in a state of superposition? It is because these objects are not isolated. They are not perfect, solitary soap bubbles floating in a void. They are living in the very heart of a storm. Every single nanosecond, an object in our world is being bombarded by an uncountable number of interactions with its environment. Trillions upon trillions of air molecules are constantly colliding with its surface. It is being bathed in a constant shower of photons from the light in your room, from the sun, from distant stars. It is radiating its own heat out into the environment. Each and every one of these tiny, insignificant interactions is a measurement. Each one is a finger, touching the soap bubble. For an object as large as a chair, it is being observed by its environment trillions upon trillions of times every single second. Its quantum state is being popped, its wave of potential is being collapsed, so relentlessly and so instantaneously that it never, ever has a chance to exist in a ghostly state of superposition at all. It has no choice but to be solid, definite, and predictable. It is locked into its classical reality by its constant, overwhelming conversation with the world around it. And this reveals the true nature of the great challenge for the scientists and engineers who are now trying to build quantum technologies. The difficulty is not in creating quantum states. Superposition and entanglement happen naturally, all the time, at the smallest scales. The true, monumental challenge is in protecting them. To build a quantum computer is to attempt the seemingly impossible. It is to try and build a perfect sanctuary for these fragile states, a place of almost absolute silence and isolation, shielded from the constant, noisy chatter of the classical world. It is a quest to create the coldest, quietest, most magnetically still places in the entire universe. It is an attempt to hold a perfect soap bubble in the heart of a hurricane, to keep it from popping long enough for us to use its beautiful, magical properties to perform calculations that would be impossible in any other way. This challenge of fragility, this constant, gentle touch of the universe that enforces our classical reality, seems like an insurmountable barrier, and for a long time, it was. But this is not a story of impossibility. It is a story of human ingenuity, for we are now, for the first time in our history, beginning to learn how to build these quiet sanctuaries. We are learning how to whisper to the universe in its own language. We are learning how to hold a soap bubble without breaking it. We have arrived at the heart of the great challenge. We have learned that the strange and beautiful rules of the quantum world are protected by a profound and delicate fragility. The constant, gentle touch of our classical world, the endless rain of light and heat and vibration, is enough to shatter the perfect soap bubble of a quantum state, forcing its infinite potential to collapse into a single, mundane reality. For a long time, this challenge of decoherence seemed like an insurmountable wall. It seemed to be a fundamental law of nature, a gentle but firm declaration from the universe that its deepest, most magical secrets were for observing only, not for touching, and certainly not for using. The quantum realm was a beautiful, ghostly dream, but our world, the world of engineering and technology, had to remain firmly planted in the solid, predictable soil of classical physics. But humanity is a species of dreamers, and for decades, a quiet, audacious dream began to take shape in the minds of a few brilliant physicists. It was a dream that went against all intuition. What if, they wondered, we did not have to accept this barrier? What if, instead of simply observing the quantum world from a distance, we could learn to participate in its dance? What if we could learn to speak to the universe in its own native language? This was the birth of the dream of the quantum machine. It is important to understand that this was not a dream of simply making our current computers faster. That is a common misconception. A quantum computer is not a more powerful version of the laptop on your desk, just as a grand concert piano is not a louder version of a single, simple flute. They are fundamentally different instruments, designed to play entirely different kinds of music. Our classical computers, the marvels of engineering that power our modern world, are, at their core, masters of logic and order. They are built upon the simple, unambiguous foundation of the bit. A bit is like a light switch. It can be either on or it can be off. It can be a 1 or it can be a 0. There is no in between. And from this simple binary language, by stringing together billions of these switches and flipping them at incredible speeds, we have built a world. A classical computer solves a complex problem by trying every possible solution, one by one, with relentless and lightning-fast determination. But a quantum computer is built upon the strange and beautiful ambiguity of the quantum world itself. Its fundamental unit is not the bit, but the qubit. And a qubit is not a simple switch. It is the unplayed melody. Thanks to the principle of superposition, a qubit can be a 1, and it can be a 0 at the same time. It can be any and all combinations of the two. It is a delicate, spinning sphere of infinite possibilities, and this single, profound difference changes everything. Because a quantum computer can hold all possible inputs to a problem at once, it can, in a sense, explore all possible solutions simultaneously. It is not trying each key on a keyring, one by one, to find the one that fits the lock. It is gently touching all the keys at once, and in a single, harmonious moment of quantum interference, it feels which one is the right one. And this power grows exponentially. If you have 2 classical bits, you can represent one of 4 possible combinations, but you can only represent one of them at a time. If you have 2 qubits, thanks to superposition and the spooky, instantaneous connection of entanglement, you can represent all 4 combinations, all at the same time. With just 300 entangled qubits, a machine so small you could hold it in your hand could, in theory, hold more possible values than there are atoms in the entire known universe. This is the source of the dream. The dream of a machine that could solve problems that would take a classical supercomputer billions of years longer than the age of the universe itself to even begin to tackle. What kind of problems? The problems that nature itself is solving, every single moment. The intricate dance of a protein folding into its perfect, life-giving shape. The complex quantum choreography of a chemical reaction that could lead to a new, life-saving medicine, or a new material that could revolutionize our world. The beautiful, chaotic patterns of the global climate. To ask these questions of a classical computer is like trying to describe a beautiful, complex painting using only the words yes and no. But a quantum computer could, in theory, simulate these natural processes directly, because it speaks the same language. It would be like asking nature a question in its own native tongue, and receiving a clear and perfect answer. This is the dream, not just of a faster machine, but of a deeper understanding. A machine that would allow us to unlock the most profound secrets of chemistry, of biology, of physics itself. For decades, this remained a beautiful but distant dream. A theoretical paradise, guarded by the seemingly impassable dragon of decoherence. But this is not a story of impossibility. It is a story of human ingenuity, for in the quietest, coldest, and most shielded laboratories on Earth, we are now, for the first time, beginning to learn how to build these quiet sanctuaries. We are learning how to whisper to the universe in its own language. We are learning how to hold a soap bubble without breaking it. And so, we are left with this beautiful, audacious dream. The dream of a machine that does not simply calculate, but converses with the very fabric of reality. A machine that speaks the strange and elegant language of the quantum world, allowing us to ask questions we have never before had the words to formulate. But every language, from the simple words we speak to each other in the quiet of the night, to the grand, mathematical language of the cosmos, is built from a simple foundation. It is built from an alphabet, a set of fundamental characters from which all meaning and all complexity can be woven. The language of our classical computers, the language that has built our modern world, is a beautifully simple one. Its alphabet has only two letters, a 0 and a 1. This is the bit. It is a light switch, which can be either off, representing 0, or on, representing 1. It is a state of absolute certainty. There is no ambiguity, no in-between. And from this simple, binary alphabet, through the sheer genius of human logic and engineering, we have learned to write symphonies of code, to build worlds of information, to connect our entire planet. But to speak the language of the quantum world, we need a new alphabet. We need a letter that can hold not just certainty, but also potential. A character that can embody the beautiful ambiguity of the unplayed melody. This new letter, this fundamental building block of our quantum dream, is the qubit. A qubit is not a simple light switch. It is something far more mysterious and far more powerful. Thanks to the strange and beautiful rule of superposition, a qubit can be a 0 and it can be a 1 at the same time. Let us try to picture this. Imagine a classical bit as a simple coin lying flat on a table. It is either heads or it is tails. It is a definite, unambiguous state. A qubit, on the other hand, is that same coin, but it is spinning on its edge. As it spins, in a shimmering, ghostly blur, it is both heads and tails at once. It is a perfect, dynamic superposition of both possibilities. Only when we reach out and stop its spine, only when we make a measurement, does it collapse into a single, definite state, landing on either heads or tails. Or think of it, perhaps, as a compass. A classical bit is like a simple compass that can only point either north or south. A qubit is like a magical compass whose needle can point in any direction, all at once. It can point north and south and east and west and every single infinitesimal direction in between simultaneously. It holds within its single, delicate state an infinite amount of directional information. This is the power of the qubit. It is a single character that contains a universe of information. And when we weave these qubits together, when we entangle them, their power does not simply add up, it multiplies exponentially. 2 entangled qubits can hold 4 states at once, 3 can hold 8. And as we discussed, just a few hundred of these spinning coins, these magical compasses, could hold more information than there are atoms in the known universe. This is the alphabet we are now learning to write with. But what are these qubits in reality? What are the physical spinning coins that our scientists are now building in their quiet, shielded laboratories? They are not, of course, actual coins. They are tiny, fragile, and beautiful pieces of the quantum world, coaxed into existence and protected with incredible ingenuity. In some quantum computers, a qubit is a tiny, superconducting circuit, a microscopic loop of metal cooled to temperatures colder than the deepest reaches of outer space. At these extreme temperatures, the electricity flows without resistance, and the circuit can enter a ghostly quantum state, its current flowing in both directions at the same time, representing both a 0 and a 1. In other machines, a qubit is a single, solitary ion, a single atom, trapped and held perfectly still in a web of invisible laser beams. Its quantum state is represented by the delicate energy level of its own internal electrons. These are the real-world alphabets of our quantum dream. And the very act of building them, of holding them in their fragile, spinning state, is one of the greatest technological challenges humanity has ever undertaken. Each qubit must be a perfect sanctuary, a tiny, isolated universe shielded from the constant, noisy chatter of the classical world that is always trying to pop its beautiful quantum bubble. We are, in this very moment, in the earliest days of learning this new language. We are like ancient scribes, just now learning how to carefully draw the first, beautiful letters of a new alphabet. We are learning how to create these qubits, how to protect them, and how to make them speak to one another through the spooky, instantaneous connection of entanglement. It is a slow, patient, and deeply humbling process. But with each new letter we learn to write, we come one step closer to composing the great sentences, the beautiful paragraphs, and the epic stories, the quantum algorithms that will allow us to finally understand the deepest secrets of the universe. And in the last few years, our progress in writing with this new alphabet has been nothing short of breathtaking. We are, in this very moment, in the earliest days of learning a new language. We are like ancient scribes, just now learning how to carefully draw the first, beautiful letters of a new alphabet. We are learning how to create these qubits, how to protect them, and how to make them speak to one another through the spooky, instantaneous connection of entanglement. But as we have learned, the very paper upon which we are trying to write, the very fabric of the quantum world, is exquisitely fragile. Our qubits, these beautiful spinning coins of potential, are like perfect soap bubbles, and the slightest touch from the outside world is enough to pop them, erasing the delicate information they hold in an instant. This challenge of decoherence, this constant, gentle whisper of the classical world, has been the great, looming shadow over the dream of the quantum machine. For decades, the primary approach to this problem was one of brute force. If the soap bubble is fragile, we must build a better sanctuary for it. We must make the room colder, the vacuum emptier, the magnetic fields quieter. We have built shields within shields, creating the most isolated places in the known universe, all in an effort to protect these delicate states for just a few microseconds longer. And in this quest, we have achieved wonders of engineering. But a new and profoundly elegant idea has begun to take shape, a different approach to the problem. What if, instead of trying to build a perfect sanctuary for a fragile soap bubble, we could learn to create a different kind of bubble altogether, a bubble that was, by its very nature, strong and resilient, a bubble that did not care about the gentle breezes of the outside world. This is the dream of the topological qubit, and to understand it, we must first think, for a moment, about the beautiful mathematical idea of topology. Topology is, in its essence, the study of shapes and their properties that do not change when they are stretched, bent, or deformed. The most famous, and perhaps most charming, example is that of a coffee mug and a donut. To a topologist, they are exactly the same shape. Why? Because each of them has exactly one hole. You can, in your mind's eye, imagine gently and continuously reshaping the clay of a coffee mug, flattening the cup, enlarging the handle, until it becomes the perfect, smooth shape of a donut. Throughout this entire process, the one essential property, the property of having one hole, remains unchanged. The number of holes is a topological property. It is a global, robust feature of the shape itself. Now, what if we could store quantum information not in a fragile, local property of a single particle, like its spin, but in the global, topological property of an entire system of particles? This is the breathtakingly clever idea behind the topological qubit. The information, the zero or the one, is not stored in a single, vulnerable place. Instead, it is braided into the very fabric of a special state of matter. Imagine taking several quantum particles and weaving their paths around each other in a complex, beautiful braid. The information is not stored in any single strand of that braid. It is stored in the overall pattern of the weave itself. Now, think what happens if the noisy outside world tries to interfere. A stray magnetic field, a tiny vibration, might jiggle one of the individual strands of the braid. In a normal quantum computer, that single jiggle could be enough to destroy the information. But in our topological braid, the overall pattern, the essential knottedness of the weave, remains completely unchanged. To destroy the information, you would have to do something far more drastic. You would have to cut one of the strands entirely. The information is protected by the global, collective, and beautiful shape of the system. The soap bubble is no longer fragile. It has been woven into a resilient, topological knot. For many years, this idea was a beautiful piece of theoretical physics, a dream on a blackboard. The special states of matter, and the exotic, almost mythical particles needed to create these braids, seem to exist only in the elegant equations of our most brilliant minds. But in the last few years, and with incredible breakthroughs announced in 2024 and 2025, this dream has begun to step out of the blackboard and into the real world. In quiet, shielded laboratories, scientists have, for the first time, been able to create and control these elusive topological states of matter. They have learned how to coax these exotic particles into existence and have begun to learn the first tentative steps of how to braid them. This is more than just an incremental improvement, it is a potential paradigm shift in our quest to build a quantum machine. It is like the difference between writing a message on the surface of a still pond, where the slightest breeze can erase it, and carving that same message into a block of granite. We are still at the very beginning of this new chapter. The challenges are still immense. But for the first time, we can see a clear path towards a truly robust and scalable quantum computer. A machine built not on fragile, fleeting states, but on the deep, resilient, and beautiful geometry of the quantum world itself. We are not just learning to protect the soap bubble anymore. We are learning how to weave a stronger thread. And with this stronger thread, we can begin to dream of the even more complex and beautiful tapestries that we might one day create. We are learning to weave a stronger thread. In the quietest laboratories on Earth, we are moving beyond the dream of simply protecting a fragile soap bubble and are beginning to braid our quantum information into the very fabric of reality itself, creating topological knots that are, by their nature, resilient and strong. But even the strongest thread can fray. Even the most perfect knot can be jostled. In our quest to build a quantum machine, we are faced with a profound and humbling truth. In our universe, there is no such thing as perfection. There will always be a stray particle of heat, a tiny fluctuation in a magnetic field, an imperfection in the very materials we use to build our delicate machines. Errors are not a possibility, they are an inevitability. For a long time, this was the final, seemingly insurmountable barrier. Even if we could build a qubit, and even if we could protect it, the slightest imperfection in our control, or the slightest whisper from the outside world, would eventually introduce an error, a tiny flaw in the delicate quantum calculation that would cascade and grow until the final answer was meaningless. The dream of the quantum machine seemed destined to be a dream of perfect, but unattainable, fragility. But what if true resilience is not about achieving a state of flawless perfection? What if, instead, it is about accepting imperfection and building a system with the wisdom to heal itself? This is the beautiful and profound idea behind quantum error correction. It is, perhaps, the most intellectually stunning achievement in our entire quantum journey. It is the story of how we are not just building a machine, but teaching it how to mend the very fabric of its own reality. To understand this, let us first think about how our classical computers, the machines of our everyday world, deal with errors. They do it through a simple and powerful idea: redundancy. Imagine you want to send a single, important piece of information, a zero, or a owned down a noisy telephone line. To make sure it arrives safely, you don't just send it once, you send it 3 times. You send 000 if, due to static on the line, the message arrives as 010. The receiver can immediately see that there is an error, and by a simple majority vote, it can confidently correct the error and know that the intended message was, in fact, 0. This is the simple, elegant heart of classical error correction. But when we try to apply this simple idea to the quantum world, we immediately run into two of its most fundamental and most beautiful rules. First, we cannot simply copy a qubit. The no cloning theorem, a fundamental law of quantum mechanics, tells us that it is impossible to create an independent and identical copy of an arbitrary quantum state. Our qubit, our spinning coin of potential, is a unique and singular entity. We cannot simply make 3 of them to create a redundant copy. And second, we cannot simply look at the qubit to see if it is in the correct state. The very act of measurement, as we have learned, collapses the wave of potential. It forces the spinning coin to land on heads or tails. If we were to read our qubit to check for an error, we would, in that very instant, destroy the delicate superposition of 0 and 1 that holds the quantum computer's immense power. We would be destroying the very information we were trying to protect. It is a beautiful and seemingly impossible paradox. How can you fix a message that you are not allowed to read? How can you mend a fabric that you are not allowed to touch? The solution is one of the most elegant and ingenious ideas in all of science. We do not measure the qubit directly. Instead, we use other helper qubits, known as ancilla qubits, to gently ask the system about its relationships without ever looking at the precious information itself. Imagine our secret quantum information is a precious, secret letter sealed inside an envelope. We cannot open the envelope to read the letter, as that would destroy its secrecy. But we want to know if the envelope has been damaged, if it has been smudged by an error. So, we take other, blank pieces of paper, our helper qubits, and we gently touch them to the outside of the envelope in a very specific, patterned way. By then looking only at the blank papers, we can see the imprint of any smudge, any error, without ever having to open the envelope itself. We learn what the error is and where it is, without ever learning what the secret message says. And with that knowledge, we can reach in and perfectly correct the error, leaving the secret message untouched and pristine. This is the essence of quantum error correction. Through the spooky, beautiful dance of entanglement, we connect our data qubits to our helper qubits. By measuring only the helpers, we can diagnose the errors on the data qubits and then apply a precise, correcting touch, all while the precious quantum information remains safely shielded in its state of superposition. For years, this too was a beautiful dream on a blackboard. But in the year 2024, in quiet laboratories around the world, this dream became a reality. Multiple, independent teams of scientists announced that they had finally, for the first time, crossed the great threshold. They had built small, working quantum error-correcting codes that actually worked. They showed that the information stored in their logical qubit, the single, abstract idea of a qubit, protected by this community of physical qubits, was more stable and survived for longer than any of the individual, unprotected physical qubits it was made from. The process of healing was now more powerful than the process of decay. The community was stronger and more resilient than the individual. This is more than just a technical milestone. It is a moment of profound significance. We are no longer just building qubits. We are now building logical qubits. We are creating a new kind of quantum entity, a resilient, self-healing piece of information that can survive the gentle, constant noise of our classical world. We are not just building a machine. We are learning to instill it with the wisdom of resilience. We are teaching the universe how to heal itself. And in this quiet, humble, and breathtaking achievement, we find a new and profound sense of peace and a clear, shining path towards the future. We are learning to teach the universe to heal itself. We are weaving resilient, self-correcting tapestries of information, creating logical qubits that can withstand the gentle, constant noise of our classical world. This journey, from understanding the fragility of the quantum state to building systems that can actively preserve it, is a story of incredible human ingenuity. It feels as though we are finally beginning to master the fundamental rules of this hidden world. But the universe, in its infinite and quiet wisdom, always has more to teach us. Just when we believe we have grasped the essence of a great mystery, it gently reveals a new layer, a deeper and more subtle truth that we had not even imagined was there to be found. And so it is with the most famously strange and beautiful of all quantum phenomena, entanglement. We have spoken of it as a spooky connection, a conversation between twin souls. We have pictured two particles, born from a single event, forever linked in their properties. If one chooses to be spin up, its twin, even a galaxy away, instantly becomes spin down. This has been our foundational understanding of this beautiful, non-local dance. It is a profound and powerful idea, and yet, it is only the beginning of the story. In recent years, as our tools for peering into the quantum realm have become ever more precise, we have begun to discover that this spooky connection is even richer and more varied than we had ever dreamed. It is as if we have been listening to a beautiful, simple melody for a century, and are only now beginning to hear the complex and subtle harmonies that have been playing beneath it all along. In a quiet laboratory at the Technion Israel Institute of Technology, a recent and beautiful discovery has illuminated one of these new, hidden harmonies. Scientists there have found a new form of quantum entanglement, a new and more intimate way for particles to be connected. To understand it, we must first refine our picture of a particle like a photon, a single particle of light. It is not just a simple point, it has complex, dynamic properties. It has a spin, which we can imagine as the particle spinning on its own axis, like a tiny spinning top. But it can also have an orbital angular momentum, which we can picture as the shape of its wave front, a gentle, spiraling, twisting motion as it travels through space. It is not just spinning, it is also dancing. The total angular momentum of this photon is the sum of this entire performance, its spin and its dance, combined. It is the complete, holistic description of its entire rotational character. Previously, we understood entanglement primarily through a single property, like spin. But this new discovery has revealed that two photons can be entangled in a far deeper and more holistic way. They can be linked by their total angular momentum. Imagine two dancers, our twin photons. In the old picture, they were linked in a simple way. If one spun to the left, the other would instantly spin to the right. But in this new, deeper form of entanglement, they are linked by their entire choreography. It is not just the direction of their individual spins that is connected. It is the sum total of their spins and their graceful orbital dances, all woven together. To know the complete rotational story of one dancer is to instantly know the complete rotational story of the other. It is a connection of profound and beautiful complexity. And to achieve this, the scientists had to create a very special kind of dance floor. They learned how to trap these photons, these particles of pure light, inside tiny, sculpted cages of matter. Structures so small they are measured in nanometers. Imagine fireflies, captured for a moment in a tiny, intricate crystal jar. Within this confined space, the photons are forced to interact with each other in new and subtle ways. And it is here, in this intimate, confined dance, that this new, holistic form of entanglement is born. This is more than just a beautiful new piece of knowledge about the universe. It holds a quiet and profound promise for the future of our quantum dream. The great challenge of building a quantum computer has always been one of scale. The components we use to trap and control single atoms or superconducting circuits are, by their nature, large and complex. But this discovery suggests a new path. By learning to encode information in these richer, more complex quantum states, like the total angular momentum of a particle, we may be able to store far more information in a single particle. It is like discovering that a single letter in our quantum alphabet can, in fact, hold an entire word, or even a sentence. This could allow us to build the components for our quantum machines on a far smaller, more elegant, and more integrated scale. This is not a race to build smaller computers for the sake of size. It is a journey towards a technology that is more in harmony with the natural world. It is a shift from building large, loud machines to creating small, quiet, and incredibly sophisticated systems. It is the difference between shouting across a vast and noisy room and sharing a quiet, intimate whisper. And so, our journey of understanding continues. Even the most familiar mysteries, the ideas that have been with us for a century, are still unfolding, still revealing new layers of beauty and complexity. The universe is not a book that we are simply reading, it is a conversation. And as we learn to listen more closely, with ever more sensitive and gentle instruments, we are beginning to hear the true depth and richness of its beautiful quantum song. Our journey of understanding continues. We are learning to listen to the universe, and in that listening, we are discovering ever more intimate and subtle conversations happening all around us, in the hidden world of the quantum. We are learning to weave stronger threads, to create more resilient forms of information, and to speak to reality in its own native tongue. But as we build these beautiful and complex machines, we are guided by a certain image of what power looks like. In our classical world, power is often associated with scale, with noise, with a great and visible expenditure of energy. Think, for a moment, of the great titans of our modern age, the classical supercomputers. They are the pinnacles of our logical binary world, and they are monuments to brute force. To house one of these machines is to build a cathedral of computation. They occupy vast halls, filled with row upon row of sleek, black cabinets, each one humming with a barely contained power. The air thrums with the constant, deep roar of the cooling systems, a man-made hurricane that is necessary to carry away the immense heat generated by billions upon billions of light switches, flipping trillions of times every second. To power one of these titans requires the energy of a small city. It is a loud, hot, and hungry form of intelligence, and it is magnificent. It is a testament to our species' ability to solve problems by building ever larger, ever more powerful engines. We have learned to fight complexity with overwhelming force. For a long time, it was assumed that the path to quantum computing would be a similar one, only more extreme. We imagined that to control the delicate quantum world, we would need even more power, even more complex cooling, even larger and more energy-intensive machines. We imagined that the power of the quantum world would be an even louder roar. But the universe, it seems, has a different and far more elegant idea of what power truly is. And in the year 2025, a quiet and profound breakthrough was announced, one that has changed our understanding of the very nature of computational power. In a shielded, silent laboratory, a new kind of quantum processor was brought to life. And it was not just faster than our classical titans, it was powerful in a completely new way. The results were almost unbelievable. This new machine, still just a prototype, was able to perform a specific, complex calculation more than 200 times faster than the world's most powerful classical supercomputer. But that was not the most remarkable part of the story. It achieved this incredible speed while consuming 2,000 times less energy. Let us pause and allow that thought to settle. A machine that is hundreds of times faster, while being thousands of times more efficient. This is not just an improvement, it is a revolution. It is a sign that we are beginning to unlock a new kind of power, a power that is not based on force, but on elegance. So, where does this incredible, silent power come from? It does not come from making the components smaller or faster. It comes from a fundamentally different way of thinking about a problem. Let us return to our metaphor of a vast library, containing all the books in the world. A classical supercomputer, for all its immense power, is like a librarian of impossible speed. To find a single piece of information, it must read every single book, one by one, from beginning to end. It does this at a breathtaking pace, but it is still a linear, brute force process. A quantum computer is not a faster librarian, it is something else entirely. Thanks to the magic of superposition and entanglement, it is like a reader who can, in a single, silent moment, read every single book in the library, all at the same time. It does not search through the information. It inhabits the entire information space at once. And through the beautiful, subtle mathematics of quantum interference, it can gently cancel out all the wrong answers, leaving only the single, correct answer to resonate, to shine through. This is the source of its silent power. It is not the roar of a great engine, burning through immense amounts of fuel. It is the quiet, harmonious hum of a system that is in perfect resonance with the problem it is trying to solve. It is the power of subtlety, of elegance, of working with the strange and beautiful laws of the universe, rather than trying to overpower them with classical force. This breakthrough is more than just a technological achievement. It is a quiet, philosophical lesson from the universe. It suggests that the greatest power is not always the loudest. It suggests that true efficiency comes not from force, but from understanding. We are beginning to build machines that reflect the very nature of the quantum world they inhabit. They are quiet, they are efficient, and they are capable of a complexity that seems, to our classical minds, like magic. This is not the loud, hot power of a star. This is the silent, cool, and deeply intelligent power of the cosmos itself. And in that quiet, efficient hum, there is a profound sense of peace. It is the peace of knowing that we are not just building tools, but are beginning to enter into a new and more harmonious relationship with the very fabric of reality. We have journeyed far into the heart of our quantum dream. We have seen how humanity is learning to speak the language of the universe, to build machines that operate not with the loud roar of classical force, but with the silent, elegant power of quantum mechanics. This is a story of active creation, of building, of computing, of asking the universe questions in its own native tongue. But there is another, equally profound, and perhaps even more intimate, side to our quantum journey. It is a story not of speaking, but of listening. It is a story not of building, but of feeling. It is the story of how we are using the strange and beautiful rules of the quantum world to develop a new set of senses for humanity, senses of almost unimaginable precision and sensitivity. This is the quiet revolution of quantum sensing. Let us think for a moment about our own senses, the 5 familiar gateways through which we experience the world: sight, sound, touch, taste, and smell. They are beautiful, and they are the source of all of our joy and wonder. But they are also, in the grand scheme of the universe, incredibly limited. Our eyes can only see a tiny sliver of the vast electromagnetic spectrum, a single, colorful octave in a symphony of infinite light. Our ears can only hear a narrow range of vibrations, deaf to the silent, ultrasonic calls of the bat or the deep, infrasonic rumbles of the earth itself. For centuries, we have built classical instruments, telescopes, microscopes, seismometers to extend these senses, to allow us to see further, to hear more deeply, and these tools have been magnificent. But even they have their limits. They are, at their core, noisy. They are like trying to listen for the sound of a single pin dropping in the middle of a crowded, bustling city. But what if we could learn to listen in a place of perfect, absolute silence? What if we could build a sensor so exquisitely sensitive that the single, gentle touch of a pin dropping would sound like a thunderclap? This is the beautiful promise of quantum sensing, and its incredible power comes from the very same property that makes quantum computing so difficult: the profound fragility of the quantum state. Remember our perfect soap bubble, our qubit held in a delicate state of superposition. For computing, our greatest challenge is to protect this bubble from the slightest touch of the outside world. But for sensing, this fragility becomes our greatest superpower. Imagine that same soap bubble floating in a place of perfect stillness. It is the most sensitive detector imaginable. The slightest disturbance, the passing of a single, stray magnetic field, the gentle gravitational pull of a single, distant atom, the whisper of a single photon of light is enough to cause a ripple on its perfect surface. It is enough to change its state, to pop the bubble. And if we can learn to carefully monitor the state of that bubble, we can detect these impossibly small disturbances. We can learn to see the world not through a noisy, classical lens, but through a quiet, exquisitely sensitive quantum window. And this is not a distant dream. It is happening right now. We are building these quantum sensors, and with them, we are beginning to perceive a layer of reality that has always been hidden from us. Consider the challenge of seeing a delicate, almost transparent object, like a single biological cell under a microscope. To see it with a classical light microscope, we must shine a bright light upon it. But that very light, that shower of photons, can damage or even destroy the fragile living structure we are trying to observe. But a new form of quantum sensing, a technique of almost magical elegance, now allows us to see an object with light that has never even touched it. Using the spooky, instantaneous connection of entanglement, scientists can create a pair of entangled photons. One of these twin photons is sent on a path that passes by the object, while the other travels on a completely separate path to a detector. By observing the subtle changes, the quantum interference, in the photon that never touched the cell, they can reconstruct a perfect image of it. It is like deducing the shape of a person in a dark room, not by seeing them, but by observing the subtle changes in the light on the far wall, a shadow of a shadow. It is a way of seeing with a gentle, ghostly touch, a technique that could revolutionize medical imaging, allowing us to watch the delicate, living dance of our own cells without ever harming them. We are learning to see the invisible, and we are also learning to feel the imperceptible. Quantum sensors are now being built that can detect tiny, almost non-existent variations in the pull of gravity. They are like a spider's web of space-time, so perfectly still that they can feel the tremor of a single, distant footstep. These sensors could allow us to map the hidden world beneath our feet with incredible precision, to see the secret rivers of groundwater, or the deep, hidden chambers of magma that lie sleeping beneath a volcano, giving us precious warnings of its intent to wake. This is more than just building better tools. This is a story of humanity developing new senses. We are learning to see with a ghostly light. We are learning to feel the very texture of space-time. We are learning not just to look at the universe, but to listen to its faintest, most subtle whispers. And in that quiet, intimate listening, we find not just knowledge, but a new and more profound connection to the beautiful, hidden world that has been surrounding us all along. We are learning to listen to the universe. With the exquisite fragility of the quantum state, we are building new senses for ourselves, perceiving the world with a ghostly light and feeling the very texture of space-time. This journey, alongside the dream of the quantum machine, paints a picture of a future that is almost unimaginable. A future where our relationship with the universe is one of deep conversation and profound understanding. But every great technological leap, every new power that humanity has ever unlocked, has always carried with it a quiet and profound duality. Fire can warm our homes, but it can also burn them down. The power of the atom can light our cities, but it also holds an immense and terrible destructive force. And so it is with the quantum machine. The very same properties that give a quantum computer its silent, elegant power, its ability to inhabit a universe of possibilities all at once, also give it the potential to become a key of almost unimaginable power. A master key, capable of unlocking the most secret and protected chambers of our modern world. To understand this, we must think for a moment about the quiet, invisible architecture that protects our digital lives. Every time you send a secure message, make a purchase online, or access your private information, your data is protected by a beautiful and clever mathematical lock. This is the world of modern cryptography. Most of the locks that protect our digital world today are built upon a single, simple principle. They are based on mathematical problems that are incredibly easy to perform in one direction, but incredibly, almost impossibly, difficult to reverse. Imagine taking two very large prime numbers and multiplying them together. Even a simple calculator can do this in an instant. But if you are given only the final, much larger number, and are asked to find the two original prime numbers that created it, that is a problem of immense difficulty. For a classical computer, even the most powerful supercomputer on Earth, to solve this problem for a sufficiently large number would take thousands, or even millions, of years. Our digital secrets are safe, not because they are impossible to break, but because it would take an impossibly long time to do so. Our locks are built upon the foundation of this classical difficulty. But a quantum computer does not think in a classical way. In 1994, a brilliant mathematician named Peter Shor devised a quantum algorithm, a set of instructions for a future quantum machine that could solve this exact problem with an almost magical ease. A mature quantum computer, running Shor's algorithm, could factor these enormous numbers not in millennia, but in a matter of hours, or even minutes. It would not be breaking the lock with brute force. It would be speaking to the lock in its own native, mathematical language, and the lock would simply and willingly reveal its secrets. The master key would turn, and in that moment, the entire foundation of our modern digital security would dissolve away like a dream upon waking. This is not a vision of the future meant to frighten. It is not a story of a coming cyber war. It is, instead, the quiet and natural consequence of a new technological age. And this is where our story takes another beautiful and profoundly reassuring turn. For this is a story not of a coming crisis, but of quiet, human foresight. Even now, as the first true quantum machines are just beginning to awaken in their shielded, silent cradles, another group of quiet guardians is already at work. They are not physicists or engineers building the machines. They are mathematicians and cryptographers, the quiet architects of our digital future. And they are not waiting for the master key to be built. They are already busy designing a new generation of locks that a quantum computer, for all its immense power, will never be able to open. This is the beautiful and forward-thinking field of post-quantum cryptography. The idea is one of profound and simple wisdom. If the quantum master key is designed to open a specific kind of lock, then the solution is to invent entirely new kinds of locks, built upon entirely different principles. The new cryptographic systems being built today are based on different kinds of mathematical problems that are believed to be just as difficult for a quantum computer to solve as they are for a classical one. It is like knowing that a master locksmith has a key that can pick any traditional pin and tumbler lock in the world. The solution is not to build a better pin and tumbler lock. The solution is to invent a new kind of lock that does not use pins or tumblers at all. A lock that opens not with a key, but with a secret melody or a complex, folded shape. The old master key, for all its power, is now useless. And this is not just a theoretical idea. In these very years, a quiet, global, and collaborative effort is underway. Organizations like the National Institute of Standards and Technology in the United States are in the final stages of a massive project to select and standardize these new, quantum-resistant algorithms. Scientists and mathematicians from all over the world are working together, openly and transparently, to build and test these new digital locks, preparing our world for the great technological shift to come. This is, perhaps, one of the most beautiful and hopeful stories in our entire quantum journey. It is a story that shows that wisdom is not just about creating power, but also about understanding its consequences. It shows that we are not just blindly rushing into a new and powerful age. We are stepping into it thoughtfully, carefully, and with a profound sense of responsibility. We are building the quiet, invisible foundations of safety and trust for a world that does not yet exist. We are crafting the locks for the doors we have not yet built. And in that quiet, proactive, and collective act of wisdom, there is a deep and abiding sense of peace. It is the peace of knowing that even as we dream of the incredible possibilities of the future, there are quiet, dedicated guardians already standing watch, ensuring that that future will be a safe and secure one for us all. We are building the quiet, invisible foundations of safety and trust for a world that does not yet exist. We are crafting the locks for the doors we have not yet built. And in that quiet, proactive, and collective act of wisdom, there is a deep and abiding sense of peace. It is the peace of knowing that even as we dream of the incredible possibilities of the future, there are quiet, dedicated guardians, already standing watch, ensuring that that future will be a safe and secure one for us all. And with this foundation of safety in place, with the promise of a secure future, we can now allow our dreams to truly take flight. We can now ask the question, what grand and beautiful structures will we build within these newly protected walls? What is the ultimate purpose of this strange and powerful new machine we are learning to create? The answer, in its simplest and most profound form, is this: we are learning to build a universe in a box. Let us think, for a moment, about the act of simulation. It is one of the most fundamental and deeply human of all our intellectual pursuits. From the earliest cave paintings that simulated the hunt, to the most complex weather forecasts that simulate our planet's atmosphere, we have always sought to create models of the world, to recreate reality in a smaller, more manageable form, so that we might understand it. Our classical supercomputers are the modern masters of this art. They can simulate the orbits of galaxies, the folding of proteins, the intricate flow of air over an airplane's wing. And they do this with incredible power, but they have always had a quiet and fundamental limitation. They are classical machines, speaking a classical language of ones and zeros, trying to describe a universe that is, at its deepest level, not classical at all. To ask a classical computer to perfectly simulate a quantum process, like a complex chemical reaction, is like asking a pianist, with only the black and white keys of a piano, to perfectly recreate the sound of a human voice. The pianist can get remarkably close. They can capture the melody, the rhythm, the emotion, but they can never truly capture the infinite, subtle, and continuous nuance of the real thing. There will always be something essential that is lost in the translation. The great physicist Richard Feynman once famously said, "Nature isn't classical, damn it. And if you want to make a simulation of nature, you'd better make it quantum mechanical." This is the beautiful, simple, and profound idea at the heart of our quantum dream. A quantum computer does not imitate the quantum world from the outside. It does not approximate it with a classical language. It is the quantum world. It is a small, controllable, and exquisitely designed piece of nature itself, one that we can use to ask questions of the larger, untamed nature that surrounds us. It is not a piano trying to imitate a voice. It is a voice learning to sing. And what songs will it sing? First, it will sing the songs of life and health. Consider the creation of a new medicine. At its core, this is a problem of molecular simulation. A disease is often caused by a single, rogue protein in the body, a tiny biological machine that is folded into the wrong shape. A medicine is a key, a small molecule, designed to fit perfectly into the lock of that protein to deactivate it. For a classical computer, finding that perfect key is a process of almost infinite trial and error. But a quantum computer could, in theory, simulate the protein and the potential drug molecule together at a perfect quantum level. It could feel, with the beautiful, subtle dance of quantum interference, how the two shapes would interact, how their electron clouds would bond. It could discover the perfect key not by guessing, but by understanding. This is a path to a future where new, life-saving drugs are not discovered by chance, but designed with a profound and fundamental understanding of the very dance of life. It will also sing the songs of a better world. It will allow us to design new materials, atom by atom, materials that could lead to perfect solar panels, capturing the sun's energy with almost no loss. Materials that could create batteries of incredible capacity, storing that energy for when it is needed. Perhaps even the greatest dream of all, a room-temperature superconductor, a material that could transmit electricity with perfect, zero-loss efficiency, revolutionizing our entire energy grid and our relationship with our planet. These are the grand, practical dreams, but our quantum machine dreams of something even larger. It dreams not just of simulating a single molecule, but of simulating the universe itself. Imagine a small, quiet, and perfectly controlled quantum system, a universe in a box. Within it, we could recreate the conditions of the first few microseconds after the Big Bang, a state of such incredible energy and density that it is beyond the reach of any particle accelerator on Earth. We could watch, in our quiet, tabletop cosmos, as the fundamental forces of nature separate and the first particles begin to form. We could, perhaps, even begin to probe the greatest mysteries of all. We could simulate the strange, warped space-time at the edge of a black hole's event horizon, a place from which not even light can escape. This is the ultimate expression of our human curiosity. It is the modern-day equivalent of our ancestors, gathered around a fire, looking up at the stars and telling stories about where it all came from. We are still asking those same questions, but we are now, for the first time in our history, on the verge of building a new kind of fire, a quantum fire, around which we can gather to find the answers. This is not a quest to play God, it is a quest for understanding. It is a deeply humble and profoundly human journey to understand our own origins, to read the first pages of the great cosmic story of which we are a small but beautiful part. The quantum computer, in this sense, is not just a tool, it is the ultimate laboratory for exploring the very code of existence. It is a new kind of telescope, one that looks not outwards at the stars, but inwards, into the very heart of reality itself.